Well, good morning, everyone, and a happy Earth Day. Um, I think we'll get started as folks trickle in. Um, so welcome to the session on ecological drought, concepts, drought metrics, and tools. So I just want to start by quotes from the legendary Kelly Redmond here, who basically says that defining drought is problematic and it's been long-standing and has never been resolved to the satisfaction of all. And drought really means different things to different audiences and different stakeholders. And in that particular article, he said, he's come to favor a simpler definition for drought, which is insufficient water to meet needs. I mean, that kind of covers everything. But I think in this term, needs is where a lot of details lie. It's where complexity and our lack of understanding of, especially in the context of ecological processes and impacts, where is the need for those systems? Also, I want to emphasize that as we think about drought, it's important to think about the whole water cycle. And water is present in the atmosphere, in the soils, in the plants, in streams, in groundwater, in different layers of the land. And the point about drought and drought impact is that deficiencies in these different components of the water cycle could indicate drought and drive drought-related impacts. And also this other point that we want to kind of really emphasize here is that the deficiency in water is influenced both by the supply and the demand side of water. And so if you look at the graphic here, the supply is coming from rainfall and snowfall through precipitation, and you're losing water in the system from evapotranspiration, runoff mechanisms, and also, and ecosystem, and through kind of percolation into deep groundwater. Another term that I really want to talk about is aridity. And again, that term is thrown around quite a bit. And it's really is a measure that accounts for both the water supply and demand elements. So supply from precipitation side primarily, and demand from the evaporative demand. So as you look at the map of country and look at the aridity measures, aridity categories, you basically you start to see that much of east is humid, whereas it gets more and more arid as you go west, and how kind of the terrain plays a role in making the system less or more arid. And it's quantified in different ways. I have just given some examples here how it's quantified, but really I think thinking about it's just the controls from precipitation from the supply and demand side of the water balance. Synonymous to aridity is the concept of water limited and energy limited regions. And you see that for the US, the maps look very similar to the map of aridity here. And again, as these terms suggest, much of the East, especially the Northeast and parts of the Northwest, are energy limited regions. They have enough water, but not that much energy. And that energy kind of relates to evaporative demand piece. So less demand, more supply, whereas much of the West is water limited. Okay, now I just want to bring the terms drought and aridification here in the slide, and especially in the context of climate change. When we hear about a particular metric having a directional trend, so here we're looking at soil moisture in the Southwest, the Central Plains, sorry, and this is Southwest, having this directional trend. So both in soil moisture and metrics such as a drought index, such as FDSI. When we see these studies come out and talk about these trends, the question is, how to appropriately qualify them. And are these changes in intensity or frequency of drought, or should we qualify them as, that the region is becoming more arid, or the extent of aridification that's happening in the region should be quantified. So yeah, this is an existing tension, and it's important that we use these terms correctly. As the climate normal is changing, how do we talk about drought? Because drought essentially is a deviation from the normal. As climate is changing, we're also seeing novel kinds of droughts emerging already, or expect them to emerge or really become more aggravated during the 21st century. So I just mentioned some of these, and this is a cool graphic from a paper by Shelley and co-authors that came out 2 years ago. And just talking about 4 different kinds of novel drought that a region may be experiencing as climate is changing. First being snow drought, where you're seeing just less snow on the ground, or shorter snow season. And even though you're getting the same amount of precipitation may be actually increasing, but much of it's falling as rain because of warmer temperatures. The second kind of drought that we are probably experiencing already and expect that to occur more in future are the droughts events are hotter. And again, it's as a direct consequence of a warmer and drier atmosphere that these droughts are now hotter. You may have also heard of mega droughts in news media and papers, and that's been talked about quite a bit. And yeah, for me, it's an interesting term because mega drought is really, again, around a long-term climate mean. You're experiencing a prolonged drought condition for several decades, from a decade, 2 decades to more. And from climate change, it could happen by changes in circulation pattern. But if it's the circulation pattern is changing for good, then the question is are we in a mega drought or totally a different climate altogether, a more arid climate, because the storm system is totally moved north, for example, and it's not going to come back south. And finally, kind of on the flip side, we have the issue of flash drought. And I'll talk about an example later in my presentation, where, just that because a warmer and a drier atmosphere is sitting on top right now, when we miss these precip events, are we getting into an intense drought stress rather quickly? So just rapidly evolving drought because of warmer and dry conditions. Okay, I'll change gears a bit and talk about drought indices. We call them, most of these indices are called the standardized drought indices. And these are, really pretty accessible in terms of when you look at these indices, they can tell us, what is the deviation from the normal. So if you look at the red, it kind of quickly tells you, it helps you indicate are we in a drought or in a pluvial situation, and how extreme is the drought. So just very easy to interpret, and that's why they are kind of widely used and widely looked at. Of course, the devil is in the detail, like how appropriate these are. So again, as I said, greater indicating departures from normal conditions. And these departures are also, in standard deviation units, so easy to understand. They allow for comparability across regions. So again, they may have different aridity, but you can compare the drought stress, the extent of drought in different regions. I think it's important to understand the sensitivities of these indices to physical and biological processes. And I think it's easier said than done. and something I'll kind of repeat again during this presentation and later on, that it's really important to know what these sensitivities are as we use them. And many of these indices work at multiple time scales. So you can look at how the drought is behaving from weeks to months to years. Here are so today we'll be just talking about select drought indices. There are many more indices out there, but we've been working on these few indices with our stakeholders, and just our experience with these indices is greater. So we just bring it out in our discussion today. And these are the Palmer Drought Severity Index, FDSI, Standardized Precipitation Index, SPEI, Standardized Precipitation Evapotranspiration Index, SPEI, Evaporative Demand Drought Index, EDDI, as we call it, and Forest Drought Stress Index, FDSI. And again, so we'll keep calling these acronyms throughout our talk today. And so it's kind of a good way to get a sense of these index from this slide. We also have a cheat sheet somewhere available, and I'll put a link for that, so you can look at it at any time if you're not sure what an acronym means. And I put out here that these work at different time scales, and they take in different climate variables as inputs. So for example, the SPEI takes just precip, whereas the SPEI takes as potential evapotranspiration, and EDDI just takes in PET. They also work as proxy for different water different components of the water balance. So the PDSI does a good job for long-term soil moisture condition. SPI is just talking about the supply side of the water balance. SPEI does both supply and demand, so it gets you to soil moisture and runoff. EDDI is just looking at atmospheric thirst. And this FDSI, again, it's only appropriate for Western forests because it's just working with cold season precipitation and warm season dryness. So I wouldn't recommend it to apply for example, to the Central Plains. So yeah, it's kind of good to know what they are kind of appropriate for. And I'll just take another minute and just talk about these indices a little more. The example from the 2017 Northern Plains drought, which was a flash drought, but a very intense drought. So if you look at this one county in the northeast corner, the Sheridan County in Montana, you see how the drought emerged. There was fairly, wet to normal conditions going into that drought. In fact, the decade before the drought started was the wettest decade in the Northern Plains region in general. So coming from a very wet condition into an extremely dry conditions. And so they missed 3 months of rain, and it get into a very, very strong drought, the most severe experience. So if you look at these different indices and see for that county and see, are these indices capturing that drought? So on top is the Palmer Drought Severity Index, and the bottom is SPEI, a 6-month SPEI. And you kind of see that the Palmer Drought Severity Index, which captures the long-term trend in soil moisture, actually didn't actually catch the drought at all. It was showing wetter conditions, but something like SPEI working at shorter time scale and sensitive to those time scales did capture the drought. I'm just looking at some other indices here. In fact, I wrongly marked it as SPEI. This is SPI, just precipitation index. And for 2017, a 3-month precipitation index ending in July is the lowest. So the most extreme dry conditions from SPEI perspective. And if you look at EDDI, 1 month EDDI in July showed the highest value of EDDI for that month. So yeah, I mean, so it again depends on what index you're looking at, what time scale you're looking at. You are capturing these events. So final thoughts, it's important to work with multiple indices and not rely on a single index to capture drought stress to your system. It's important to evaluate sensitivities of these indices to impacts. And it's, again, easier said than done. Quite a bit of research is needed. And sometimes we just don't have good ecological impacts data to kind of have that, that understanding. And with that.